Welcome to the Mathematician's Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we're making personal opinion comments about someone significantly more famous than myself. It's Pappus! But first, I used to have a friend who was a linguist. Every day he would ling, and sometimes after he had langed too much, he would stop to read a book. Honestly, I have no idea what a linguist is or what he does all day, but he assures me that linguistics is a quantitative science, so I guess that makes it a type of maths? He had the unfortunate position of being born in a time where all the languages had already been invented. He graduated with a PhD and moved to Chile to do some postdoctoral work. But it turns out they already had a way of talking to each other over there. So what are you meant to do when you're really passionate about something, but come at the end of a period of nearly 1,000 years of other people doing the thing you love doing? For my friend, he learnt to dance the cuaca. But for many people, they would content themselves by reading about the work that other people in history did, making personal comments about the quality of this work, and then writing up their thoughts, perhaps as a podcast, and never really doing anything original or useful themselves. Not my friend the linguist, though. He started writing new languages, in the hope that centuries from now, after those languages get translated into whatever they speak in the future, future linguists will be able to use them to discover much of the rich culture that Chile has to offer. Pappus was born in 3 different years. Okay, obviously he was not, but this does give me an interesting opportunity to talk about how we know about various people being born, and thus the chronological order with which we explore the mathematicians. There are only 2 recorded entries that we have that give us the ability to date Pappus, or should I say determine when he was born. Those of you wishing to date Pappus perhaps need to rethink your standards. There is a reference in the Pseudo-Lexicon, a work of 10th century Greek lexicographer, which states that Pappus was a contemporary of Theon of Alexandria, a mathematician we have not yet covered and also will not cover. But then Theon of Alexandria wrote a brief history, obviously in table format because he was a mathematician, and cited Pappus as being a contemporary of Diocletian about 100 years earlier. To us, and indeed to the author of the Suda, they may as well have been contemporaries, but both sources cannot be simultaneously true, and indeed neither are. Instead, historians have done a delightfully mathematical thing and read Pappus's commentary of Ptolemy's Almagest, wherein he remarks that the eclipse of the sun in Alexandria, which took place on the 18th of October 320 CE, obviously that date is using our modern calendar, but given we know which eclipse took place in Alexandria and when, we can back calculate the day with fairly decent accuracy. So yes, Pappus was a mathematician and schoolteacher around the 4th century in, let me check my notes here, also in Alexandria. In fact, this episode is sponsored by the Tourist Board of Ancient Alexandria. If you are only ever a 14-hour flight and 1800 years away from visiting Ancient Alexandria, check out the show notes for a 20% off checkout coupon. Pappus was arguably one of the last great Greco-Roman geometers. The tide had been slowly turning towards a new and exciting algebra that we introduced last episode with Diophantus. Also, through the Roman era, there was significantly more time given to astronomy and astrology, to the point where geometry felt like a completed field. Surely we have now calculated every theorem there is to know. Spoiler, this arrogance of the current state of knowledge is not going to disappear anytime soon. So, if you were looking around you and realised that your favourite field of interest had not been significantly added to in the last 200 years, and perhaps you were going to be the last great hero of your field, what would you do? For Pappus, the answer was write a collection of all the works he could. He called this the Synagogue, which is the same word we use for the Jewish gathering. It simply means an assembly. The historian Heath describes the synagogue in this way. Obviously written with the object of reviving the classical Greek geometry, it covers practically the whole field. It is, however, a handbook or guide to Greek geometry rather than an encyclopedia. It was intended, that is, to be read with the original works, where still extant, rather than to enable them to be dispensed with. End quote. The Synagogue was divided into 8 books, each of which is introduced as though it is a new work, so we can take them as a loose compendium. They are possibly one of the earliest examples of a maths book being written as a history of, rather than simply the maths of. Not bad for the 4th century. But lest we forget, at the time of Pappus, we are now a full 1,000 years from Thales of Miletus, the starting point of the Hellenistic thinkers. This is like me doing a maths history podcast about Ibn Sina, or Avicenna, and a future historian saying he was a contemporary of myself. And if there are any hyper-evolved octopuses listening to this in the year 4500, Ibn Sina and I went to school together. So Pappus wrote a history book. Book 1 was about arithmetic, and oh so sadly, it was lost to history. Sorry guys, we aren't going to be able to do some ancient multiplication. Bummer. Book 2 is where we get Apollonius' method for dealing with large numbers and the myriad problems that were unleashed. Go back to episode 29 to hear more. Again, a good deal of this book is lost, so we only have half the story. Book 3 is where the story really gets going. In the first 2 parts, Pappus works on finding the mean proportional between 2 straight lines. At this point, I would like to quote directly from a translation of the introduction. I should warn you though, this is some difficult text to follow. Indeed, I had to reread it myself several times in order to understand what on earth Pappus is trying to say. Here goes. Those who wish to determine more artfully things sought in geometry, most noble Pandrosion deemed it right to call a problem. This is a Greek word that roughly translates to something proposed. That for which it is proposed to make and to construct something, and a theorem that in which, when certain things are supposed, what follows them, and what altogether consequent on it is observed, with some of the ancients saying that all are problems and other theorems. And so, someone putting forward the theorem, after detecting in whatever way what follows this, might consider it proper to seek it, and would not sanely put it forward in any other way, while someone putting forward the problem, if he is ignorant and an idiot, even if he prescribes what somehow cannot be constructed, is forgivable and not accountable. For it is the job of someone investigating also to determine this, what's possible and what's impossible, and if possible, when and in how many ways it is possible. But if someone laying claim to mathematics is proposing without any experience, he is not outside guilt. Well then, some of those recently, through you, laying claim to know mathematics have, ignorantly to us, determined the statements of problems. We are required to state some demonstrations about them, and things near to them for your gain and for the gain of lovers of learning in this, the 3rd book of the collection. And so, someone with a reputation for being a great geometer ignorantly determined the first of the problems. For, given 2 lines, he claimed he know how to get 2 mean proportionally in continuous proportion through a plane investigation. And the man even considered it proper for us, after examining it, to give a response about the construction that he brought about, which goes like this. I should note that that was only 2 sentences there that I read out. They didn't really like separating their prose into neat, digestible parts. But in this passage, Pappus is, in essence, delivering a stern lecture to a contemporary female mathematician named Pandrosion. Now, we've not talked about her yet. She was a maths teacher and headed her own school. Born much earlier than Hypatia, who is often regarded as the first female mathematician, it should be noted that Hypatia was not. Plenty of women have been doing excellent work in mathematics for a long time prior. Sadly, the reason that Pandrosion will be skipped, and a few other women we have met but also skipped, it's because her work did not survive to modern times. Perhaps her contribution was too small, or, more likely, patriarchy. It is notable that one of the only references we have to her is Pappus mansplaining how to do mathematics. He criticises one of her students, a man with a reputation as a great geometer, for incorrectly claiming to have solved a famous geometrical problem. Pappus uses this student's error as an opportunity to patronise Pandrosion on the fundamental principles of mathematics, asserting his own expertise in the process. At its core, Pappus's argument distinguishes between two types of mathematical propositions, problems and theorems. He explains that a problem is a proposal to construct something. A crucial aspect of a problem is that the proposed construction might be possible or impossible. It is the investigator's responsibility to determine which is the case. In contrast, a theorem involves taking existing assumptions and logically demonstrating what necessarily follows from them. Pappus argues that someone who proposes a theorem that turns out to be false is worthy of blame. However, he suggests that a person who proposes an impossible construction in a problem might be forgiven, as it is the task of the skilled geometer to figure out the limits of possibility. The heart of the criticism lies in the final paragraph. Pappus accuses one of Pandrosion's students, a man he sarcastically refers to as having a reputation of being a great geometer, of ignorantly presenting a solution to a famous problem, and this problem was to find the two mean proportionals in continuous proportion between two given lines. Now, you might remember this as a famous issue from episode 16 on monachimus. If we have lengths a and b, then two mean proportionals would be ax and ax squared, such that ax cubed is equal to b. So it's like finding the points of a multiplicative progression that divides the length ab into three sections. Monachimus showed that if this can be done, then one can double the cube. So claiming that a planar construction has been found is a big statement. As we now know, a planar construction that is one only with a compass and straight edge is actually impossible for the doubling of the cube. So, in essence, Pappus is saying to Pandrosion, your student, who thinks he's a great geometer, has made a basic and embarrassing mistake. He's claimed to have solved an impossible problem using simple tools, and this shows a lack of true understanding. As his teacher, this reflects poorly on you. And now I, the great Pappus, will proceed to demonstrate the correct way to approach these kinds of problems for your benefit and for all who genuinely love learning. Thanks, Pappus. We very nearly had an opportunity to show that female mathematicians of antiquity were respected and their contributions equal to that of the men, and instead we got you. Following on from this intellectual smackdown, Pappus did have some interesting summaries of problems and their solutions. And again, I have the pleasure of quoting him from a translation. The ancients... Pause here for dramatic irony. The ancients say that there are three kinds of problems in geometry, and some of them are called plane, others solid, and others linear. And so, those that can be solved through straight line and circular arc of a circle might fittingly be called plane, for the lines through which such problems are solved also have their coming to be on a plane. And those problems that are solved when one or more of these sections of a cone are employed for the discovery, they are called solid, for it is necessary for the construction to make use of the surfaces of solid figures, I mean of conics. A third kind is left, which is called linear, for there are other lines besides those mentioned are taken for the construction, as they have a coming about that's more intricate and constrained, such as happens to be the spirals and quadrices and cochleoids, and the cissoids, that have many and unexpected symptoms. Now, you may have missed the beautiful part in this. In the first two descriptions, we see the standard planar solutions of a compass and straightedge. A solid problem is the same rules, but with the added dimension of 3 dimensions. But then the linear problems is the sum collection of all other lines and curves that can be drawn. It is not so rigorously well defined, and there is not a textbook that expounds on all of the solutions derivable from the constructions, but we have a foundational recognition of a more organic type of geometry, the geometry that grows from the world itself. Later in the book, he goes on to cite Eratosthenes, Nicomachus, and Hero of Alexandria. Towards the end of this part, he then gives his own solution to the doubling of the cube. However, this is a break from the Euclidean rigour we have come to know and love, as he allows himself to approximate the solution by an infinite progression of repetition and improvement, converging on a solution, a linear type. Or perhaps another way of viewing this is if you can measure two things simultaneously so that they are drawn to be equal, then it is possible. However, this construction would require a moving piece and therefore breaks the Euclidean planar rigour. In the second part of Book 3, he does give a pleasing construction of the arithmetic, geometric and harmonic means. So for those of you who didn't have me as your teacher, you might not have been introduced to these in your GCSEs. The arithmetic mean is the one where you add up the numbers and divide by the number of things. That's for averaging quantities that are additive in nature, like money. This is the one that we just call the mean. The geometric mean is the one where you multiply the values and take the nth root of the product, and this is for averaging values that are multiplicative in nature, like interest rates. And the harmonic mean is the one where you reciprocate the sum of the reciprocals and multiply by the number of things that there are, and this is for summoning the demon of maths to do your bidding. Later, in Book 3, he talks at length on some paradoxes of the maths in Eryxenus' work. We have not discussed this on the show so far, and that is in part because this is the only source we have in history that mentions Eryxenus. And then, more pleasingly, he finishes Book 3 with some projections of the Platonic solid onto the inside of a sphere. In Book 4, he talks more about the linear type of problem, so that is the geometry of moving curves, those not formed by lines, circles or conics, and this includes using the quadratrix of Hippias to trisect the angle. In Book 5, we get the first mathematical account of bees constructing a hexagon, as well as the solids of Archimedes. We also see a proof of Zenodorus' theorem about the shape of equal perimeter and the greatest area of these shapes. Hashtag no spoilers. In Book 6 and 7, he makes a commentary on Theodorus, Autolycus, Aristarchus, Euclid, Apollonius, Aristaeus, and Eratosthenes. A veritable who's who of big names on campus. You might notice here that Aristaeus is the only one on that list that didn't get an episode. Do a Google, find out why. By analysing the works of the former greats, Pappus is trying to distill how we go about mathematics. And I'll quote again. In analysis, we suppose that which is sought to be already done, and inquire what it is from which this comes about, and again, what is the antecedent cause of the latter, and so on until, by retracing our steps, we light upon something already known or ranking as first principle. But, in synthesis, proceeding in the opposite way, we suppose to be already done that which was last reached in analysis, and arranging in their natural order as consequents what were formerly antecedents, and linking them one with another, we finally arrive at the construction of what was sought. So this is a comparison of the two types of mathematics, analysis and synthesis, which are essentially the same idea but going in different directions. So with analysis we start at the end and work backwards until we get something that is a first principle, but in synthesis we start with things that are known and try to create something new in a forwards direction. In Book 7 we also meet the Pappus problem. So roughly spoken, this is if you draw two lines and then make a hexagon by alternating corners on these lines, then the intersections will also form a straight line. This problem was allegedly plagiarised by Paul Gildin in the 1600s. I can't blame him, it's beautiful and fun to draw. And in Book 8 he talks lovingly, if not originally, about mechanics. Alongside this work, Pappus also wrote a lengthy commentary on Ptolemy's Almagest. Luckily, little of it survives. I say luckily because his contributions to the Almagest were lengthy and unnecessarily pedantic at best, or factually inaccurate at worst. My impression of Pappus, as you might have guessed, is one of lower esteem and respect than some of the other more notable mathematicians we have dealt with. This is because he chose to introduce himself to the world by being disrespectful to, what history has determined, a rarity of an ancient female mathematician. Or perhaps because his maths is just a little dull. Perhaps I can speak to something interesting he did leave for us then, and this is the Pappus Chain. So the Pappus Chain is a construction of circles with some intriguing properties. If we first draw a large circle, and then draw another circle inside, it is now possible to draw a set of circles such that each new circle is drawn in cotangent with the first interior circle and the external circle and the previously drawn circle. When such a chain of circles is formed, it should wrap around the first interior circle. And what we're interested in is when this wraparound forms one continuous chain, or when it is not possible so that every circle is touching four others. The answer here is sometimes. And there are some rather pleasing situations where you can find a chain of length n. I believe the smallest possible value of n is 3, but any integer value should be possible. In truth, this construction is actually the construction of the Steiner chain from Jacob Steiner, who defined them formally in the 19th century, although I can't really imagine he was the first to play with them. But a particularly interesting case of the Steiner chain is the more standard Pappus version, and in this version of the problem, we make the first interior circle at a tangent to the exterior circle, so they touch each other, and there's chain of smaller circles then that we draw in the arbolos inside should become infinitely long, and this has some unexpected properties. The centres of all of these smaller circles will be on a common ellipse, which is a more curious property when combined with the fact that a circular inversion, which is a bit like a reflection in a circular mirror, an inversion of the Pappus chain will lead to a vertical stack of congruent circles. It's a fun quirk, but maybe more recreational maths than anything terribly useful. So, whilst I don't really like Pappus, it is worth noting that he did still have a big impact on the world of 17th century European mathematics. He moved over to the Arabic world along with the rest of the canon of the mathematical literature and saved many mathematicians from obscurity by documenting their work, and we will explore this impact on Islamic scholars in due course. Naturally, European academics lost his work, and so it took until Federico Comandino in the 17th century to translate him from Arabic to Latin, where he helped to kickstart analytic geometry with Descartes and Fermat. In fact, it was his hexagon problem that gave significant motivation for this work of analytic geometry. Other mathematicians influenced by Pappus were Pacioli, Da Vinci, Kepler, Van Riemann, Pascal, Newton, Bernoulli, Euler, Gauss, Gergon, Steiner and Poncelet. So, a broad coalition of mathematicians, ancient and future. He really was the bridge between two worlds. And that's it for today's episode on the Mathematicians podcast. However, I think there is perhaps a little more housekeeping that needs to be done before I say goodbye. So, this is episode 40, and we nearly got to talk about the second female mathematicians that I've come across so far. That's Pandrosion. She does not have enough accessible resources for me to research and produce into a full episode. So, I am sorry, Pandrosion, you don't get one. But I really should stress that she would have been significant in her time. She was the head of a gosh darn school. Women in history mattered, and sadly they have been written out of much of it. And yes, I'm aware that I'm contributing to that by not telling their story, but the bits I can find wouldn't fill much longer a story than this rant that I'm doing about the poor state of women in history. I sincerely hope that if there are any women listening to this, more so the young girls considering if maths is for them, yes, it absolutely is. Don't listen to Pappus, he was an arse, as are most of the men in history. But there are still loads of cool things to be discovered in maths, and maybe you can be the woman that does that. With that said, next episode we will be talking about Hypatia, who is largely held up as the first female mathematician. This is of course a lie, there were loads, but she will be the first woman I will be discussing in a full episode next week on the Mathematicians podcast. But don't go anywhere, I'm still talking. This is episode 40. And I had always intended to do 50 episodes as my New Year's resolution back in December 24. Looking ahead then, there are about 10 names on my list left that I could string into a complete episode before we start to hit the big turning points. So I am in the year 300 CE right now, and that gives us roughly 250 years before the Prophet Muhammad, peace be upon him, is born. and then a few more 100 years before the Islamic Golden Age is in full swing, starting during the reign of the Abbasid Caliph Harun al-Rashid, so let's call it 800 CE, with the inauguration of the House of Wisdom. So I might make it through all of the pre-Islamic maths by the end of the year. Now, I've enjoyed doing this podcast. It's been a lot of fun, but the weekly schedule has been more demanding than I can keep up with. So after episode 50, I will be issuing episodes on an as-ready basis. Maybe fortnightly, maybe monthly. Maybe I'll just stop one day without saying goodbye and come back in a few years' time. Now, might be a good time to say this. Mrs. Cornish and I are expecting our second child. I'm trying to be an excellent father, and I'm trying to be an excellent husband, and as a result, podcaster is slipping lower and lower on my list of priorities of things to do each week. And this is going to roughly coincide with episode 50 coming out. So after episode 50, things will be slowing down. I'm also going to have a choice when we hit episode 50. So far, the strands of the show have been very deliberately chronological order, sticking with the Mediterranean tradition, so that is the Egyptians, the Greeks and the Romans. You'll notice I skipped most of the Babylonians and earlier because I don't know their names. The whole point of this is the mathematicians whose names that we know. But we've been staying in the loose bubble of the Mediterranean world. And I say loose because it's really a permeable membrane. Mathematicians were walking all over the place in the ancient times. And so a lot of ideas can be traced potentially from other traditions. So we see Pythagoras getting some influences, of course, from the Babylonians, but also potentially from further afield, from Indian mathematicians. It's hard to be definitive about this, and sometimes we make presumptions that aren't there simply because it feels convenient. But we do know that in the time of Alexander, the Hellenistic Empire, the Macedonian Empire, spread all the way over to India. So it's not unreasonable that a lot of information and philosophy could have spread around. But I've been sticking with the Med, and you might think then it would be a very natural transition to just move the theatre over to the Arabic world and continue the story. But this is not going to be the view from over there. In the Islamic territory, they draw their wisdom not exclusively from the Greeks, but from the vast empire that they covered and the boundaries of that. So it might make more sense to go back 1500 years, back in time, to meet Buddhayana and start following the thread of Indian mathematical tradition until the two strands eventually meet back up in Baghdad. I've always intended to give the histories of other traditions an equal respect. I'd love to cover China and the Americas in more detail. I'm not sure whether now is the right time to introduce the Indian tradition. We'll see. If you have a strong opinion one way or the other with where you'd like this history story to go, then please get in touch with me on Blue Sky at mathematicians-pod. I'd love to hear from you. So, where were we? Next week, Hypatia, 10 weeks' time. I start to slow down to look after Mrs. C and get ready for baby C. And in the meantime, I guess I start researching Arabic and Indian maths to see which one is easier to write about. Until then, goodbye! The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.